Thank you very much. Good morning, everybody. I'm very happy to be here today. I would like to thank the organizers for this invitation to share with you some of the studies that we have done since few years now in this laboratory of molecular electrochemistry here in Paris City. And so I'm going to discuss about the interest of transparent nanostructured electrodes combined to UV visible absorption spectroelectrochemistry to elucidate mechanisms. And to start my presentation, I want just to introduce those of you who are not aware of this use and preparation of functionalized nanostructured transparent electrodes, which can be either conductive or semiconductive, and they find a wide range of applications in dye-sensitive solar cells, photoelectrocatalysis, artificial photosynthesis, biosensing, and so on. So basically, they are usually made from a commercial transparent electrode, which is a glass substrate covered by a thin, dense film of a transparent conductive oxide, which is a metal oxide usually doped, such as indium tin oxide or fluoride tin oxide. And then on top of this transparent conductive electrode, a porous film will be deposited by various kinds of engineering processes. And this film can be made either of a semiconductive material, such as titanium dioxide, tin dioxide, or a fully conductive material, such as indium tin oxide or FTO itself. And this allows to get a high surface area transparent electrode. And next, you can add a functionalization step, okay, and it will allow for a high load of a functional molecule, such as a dye or a catalyst. And you get a functionalized nanostructured transparent electrode delivering a high current flow that you can use for applications that are going to combine visible light absorption and electron transfer. And I would just like to highlight here two emblematic applications. One is the dye-sensitive solar cell that were initially developed by Oregon and Gretzel. And basically the principle here is that you have a nanostructured, so I'm just testing this, yes. Here, you have here a transparent nanostructured electrode, which is made of semiconductive titanium dioxide nanoparticles, and they are functionalized by a dye, okay? And upon proper band alignment and potential alignment, what's happening is that when you shed light on the dye, then you trigger electron transfer, and this drives a photocurrent. So the second example I really like for this application of transparent nanostructured electrode is the one that was published a few years ago by Erwin Reisner groups. And it's about photoelectrochemical water splitting. And in this specific case, what they use is a transparent, fully conductive porous electrode made of indium tin oxide that is used as a transparent conductive support to immobilize enzymes. And the two enzymes immobilized are on one side photosystem 2 and on the other side hydrogenase. And this allows, because of photosystem 2, okay, you can drive photooxidation of water to dioxygen upon light absorption, and this allows water splitting at a bias that is far below the thermodynamic potential that is usually required for water splitting. So for this kind of functionalized nanostructured transparent electrodes, what I would like to show you today is that UV visible absorption spectroelectrochemistry is an interesting tool to investigate the electrochemical reactivity, and this thanks to the cross-correlation of spectroscopic and electrochemical data. So my presentation will be divided in two parts. In the first part, I'm going to discuss about catalysis at a functionalized glad indium tin oxide electrode. And in the second part, I will address the specific case of a functionalized semiconductive glad titanium dioxide electrode, at which we have both catalysis and charge storage. But first of all, I have to introduce you to this nanostructured glad electrode that we are using. Okay, so in our group, we're working with nanostructured transparent electrodes, which are prepared by a simple physical vapor deposition method. This is made by our collaborators, Michael Brett and Kenneth Harris in Canada. And the principle of this deposition process is that the vapor flux arrives with a very high angle regarding the substrate, which is furthermore rotating, and this allows for deposition of porous films. And in this specific case, we work with nanocolumnars thin films, okay, and the nanocolumn, they grow perpendicularly to the transparent conductive substrate. And the advantage of this kind of technique is that you have a very controlled and open porosity for this film, an adjustable thickness up to a few micrometer thick, and a high reproducibility. And the surface enhancement of the metal oxide film that can be deposited is directly proportional to the film thickness and is depending on the glancing angle of the deposition process. And we mainly work with two kinds of nanostructured transparent electrodes, polycrystalline indium tin oxide film, and each nanocolumn here is constituted by very small crystallites of indium tin oxide, and the surface enhancement is typically 60-70 per micrometer of film thickness. And we also work with amorphous titanium dioxide films, which are also constituted by very small particles of amorphous titanium dioxide, and the surface enhancement in that case is much larger. So next, how to get now functionalized electrodes based on these metal oxides? Well, we worked mainly with metal ion porphyrin derivatives as biomolecular redox-active chromophore or catalyst. And this, we selected these molecules because they have a very intense solid band in the visible range around 400 nanometer that is sensitive to both the redox state of the metal ion as well as its coordination state. So for the modification, you can either use simple physisorption of biomolecules thanks to multiple anchoring groups. You have satisfactory, let's say, stability. You can make something that is more stable with chemisorption of phosphonate derivatives. And you can also electrograft aryl diazonium salts to prepare these functionalized electrodes. And in my presentation here, I will mainly focus on this kind of two porphyrins. One is microperoxidase 11, which is an iron porphyrin, and the other one is a manganese porphyrin. But whatever the methodology used to functionalize the nanostructured electrode, what we demonstrated is that you have a very homogeneous distribution of the catalyst of the chromophore throughout the entire film thickness of the electrode, and so the surface coverage that you can reach is directly proportional to the film thickness of the electrode. So what's happening next if we use typically this kind of redox-active chromophore and we immobilize it in a glad indium tin oxide electrode? So for that purpose, we use an electrode that has a film that is 500 nanometer thick. Okay, it has a surface enhancement of 35, and we get this kind of surface coverage for the manganese porphyrin. And we use a very simple, and I want to emphasize this, that spectroelectrochemistry can be very easy to operate, because in this specific case, we just modify a classical UV visible absorption cuvette, okay, to enter a 3-electrode setup inside. And we work in the transmission mode, and so we simultaneously record the electrochemical information and the spectroscopic trace of the immobilized chromophore, okay? And this is a real-time methodology with a millisecond time resolution. So from electrochemistry, here in cyclic voltammetry, we get the typical voltammogram, okay? And what you can immediately notice is that you have a very high capacitive current. And this is the price to pay, because you have now a high surface area conductive electrode, right? And on top of it, you can see the Faraday current that corresponds to the redox probe. Okay, and I said now we can have simultaneously an absorbance trace as the function of time, and if you select properly your absorbance, this allows to monitor directly what's happening at the redox active chromophore, and here in that case, the reduction of manganese 3 to manganese 2, which is here reversible. This is what we call a cyclic volt absorptogram, so absorbance versus potential, and if we derivate this versus time, we get what we call a derivative cyclic volt absorptogram. And what you notice here is that this is morphologically equivalent to a cyclic voltammogram, but free of capacitive current, because you just focus on the electroactive chromophore, okay? So based on this, you can make an easy analysis of the interfacial electron transfer process, okay, even at low surface coverage of the immobilized redox probe, and you can quantify and get all the information about this reversible electron transfer. Okay, what is maybe more interesting is to look what's happening now under turnover conditions, okay? And in this specific case, we analyzed the reactivity of this chromophore toward dioxygen reduction. And porphyrins are widely used for their catalytic activity toward dioxygen reduction, CO2 reduction, and so on, okay? So in that case, what you have now is from cyclic voltammetry, you have the catalytic current, okay? And you can see here that you have a huge enhancement of the current intensity, and at some point you have a peak here, meaning that you start to be now limited by mass transfer of the substrate that has to reach the electrode. And from the DCVA now, where you still follow, remember, the formation of the reduced form of the catalyst in the film, you can notice that you have a small delay here in the accumulation of the manganese 2, but still you accumulate very rapidly the reduced state of the catalyst, meaning that in fact you have a very fast catalyst that is limited by mass transport, and in your electrode you still accumulate a lot of the reduced form of the catalyst because it's not directly involved in the catalytic process. Only a very small amount of it is involved. Meaning that in this specific case, I have to confess that UV visible absorption spectroscopy is not very useful to investigate the catalytic, the state of the catalyst under turnover conditions. And to demonstrate the interest of the technique, I have to move to another redox probe, which is in this time microperoxidase 11, which is also immobilized in a glad indium tin oxide electrode. And you get the same, it's also active toward dioxygen reduction, so you also get here a huge current intensity under catalytic turnover conditions. And from the DCVI, where you now follow the accumulation of the iron 2 state of the catalyst in the nanostructured electrode, what you notice is that you have now a delay in the accumulation of the iron 2 in the nanostructured electrode, and it only starts when the electrode is depleted by dioxygen, so you are limited by mass transport. And I will show you that now this allows to unravel the catalytic process and track for reactive and catalytic intermediates. So I have to make a long story very short, so I'm sorry for this. I just want to, okay, we investigated by cyclic voltammetry and cyclic voltabsorptometry the catalytic process at different scan rates, up to 1 volt per second, and you have here very specific shapes, especially for the accumulation of iron 2 in the nanostructured electrode. We developed a model, and we were able to fit all the experimental data, or to simulate, let's say, all the experimental data, to extract 4 parameters that are characterizing the catalytic process, including the stoichiometry of the process, allowing us to conclude about a 2-electron process reduction to hydrogen peroxide by this iron porphyrin. But what is more interesting here, and what I want to emphasize, is the distribution of the catalyst in the nanostructured electrode at high scan rate once you reach the reverse potential. And what you can notice here is that at this reverse potential, which is a very low potential, right, you have neither the resting iron 3 state, neither the reduced iron 2 state, but what you have accumulated in the network is now an intermediate state, which is an iron 3 hydroperoxide, which is the state of the catalyst that is associated to the rate limiting step of the catalytic process. Okay, so this is for the interest of this technique for operando, let's say, analysis of a catalytic process and quantitative analysis of the catalysis mechanism and identification of a catalytic intermediate. And now I move to the second part of my presentation, which is what's happening. And I want to come now back to this manganese porphyrin that I initially presented you. And what's happening if now, instead of immobilizing this porphyrin in a fully conductive glad indium tin oxide electrode, I now immobilize this porphyrin in a semi-conductive glad titanium dioxide electrode, right? So what we have shown previously that in indium tin oxide, and this is what I already showed you, we have a reversible electron transfer at the interface. We have a huge capacitive current for the high surface area electrode, and we can get all information about the reversible electron transfer, which is centered, obviously, at the formal potential for the manganese 3, manganese 2 redox transition. And now what you can see is that the data that we can record at the semi-conductive titanium dioxide electrode are completely different, right? It's not very obvious from the cyclic voltammetry that we indeed have a Faraday current. If you compare the blue one, which is with the manganese porphyrin, and the black one, which is without. Okay? But from the DCVA, where we follow accumulation of the iron 2 state, we confirm that we indeed have a reduction process. And this reduction process, it appears first to be irreversible, and second to be significantly downshifted in terms of potential compared to the formal potential of the manganese 3, manganese 2, manganese 3, manganese 2 redox couple. And to understand this, we have to come back to what is titanium dioxide as a semiconductive electrode. And this is characterized by a specific band distribution, okay? And you can indeed reach a conduction band, but this conduction band is at a quite low potential in aqueous electrolytes, meaning that over the largest part of the potential window in water, titanium dioxide is electronically insulating. And if it's electronically insulating, it cannot transfer electrons to an immobilized redox probe, right? So there is no way that you can reduce or reoxidize some manganese porphyrin at this specific potential, which lies, for example, here, if I compare to the band structure of titanium dioxide. But what's happening with titanium dioxide is that now, if you apply a reductive potential, you can electrochemically dope the material, and you start by filling some electronic traps in the band gap, and finally you reach the conduction band. And once you get the conduction band filled, then it behaves just like a metal-like electrode. So you have this reductive electrochemical doping of titanium dioxide, which is associated to an accumulation of charges, electron and protons in that case, in titanium dioxide, and it's also associated to an electrochromic properties of the material that we can now follow around 800 nanometer, which is what you can see here. Okay? So this is the trace of electron-proton accumulation in titanium dioxide. So under these conditions, we spend a lot of time to develop models and investigate this kind of interfacial electron transfer, and we developed a model for quantitative analysis of this electron transfer from this derivative cyclic voltabsorptogram, and we could extract the parameters of this irreversible interfacial electron transfer. Okay, so next point is what's happening now if we add the catalytic process in this semiconductive titanium dioxide, just like we did for indium tin oxide. Okay, so now we still have a catalytic current, so the molecule, the porphyrin, is still active for dioxygen reduction, right? We have a delay in the accumulation of the manganese 2 state, and we notice here, if we follow specifically what's happening at the titanium dioxide electrode now, okay, because now we have a technique where we follow, depending on the wavelengths, we focus either on the catalyst or directly on the metal oxide itself. Okay, so we get two different information. We deconvolute what's happening here in electrochemistry. And what we notice here is that we also have a delay in the charge accumulation at the titanium dioxide that now only starts when the electrode is depleted with dioxygen, so once we are limited by mass transport of the substrate. And to better highlight this process, we moved to chronoabsorptometric measurements. So what we did is we applied a very negative potential for a short time, okay, 15 seconds. And at this very low potential, what we assume is that we have a very fast catalytic process because the interfacial electron transfer is extremely fast, so we very rapidly deplete the electrode with the substrate. And we see that we accumulate the manganese 2. Here we focus on manganese 2, either under oxygen or under air. And here we focus on titanium dioxide. So we monitor charge accumulation in titanium dioxide now. Okay? And after this reduction step, what we do is we apply either a 0-volt potential. And when we apply a 0-volt potential, this leads to a very fast electrochemical discharge of titanium dioxide. Okay? And what we notice under these conditions is that we have then a reoxidation of the manganese 2 catalyst by the incoming flux of dioxygen, okay, which is what we expect. And if we leave the system under open circuit voltage, what's happening now is that we have a significant delay, as we can notice here, in the reoxidation of the manganese catalyst by the incoming flux and dioxygen. And this correlates now with the fact that we have stored a significant amount of charge in the titanium dioxide electrode, and that the titanium dioxide is acting as an electron reservoir to pursue catalysis, even if there is no more reductive potential that is applied to the electrode, okay? And we need now time to discharge chemically the titanium dioxide electrode through the catalytic process in order to recover the manganese 3 state of the catalyst. So this is the first example of an interplay between charge storage at a semiconductive electrode and a catalytic process at an immobilized porphyrin. And now I reach my conclusion, and I hope I have convinced you that UV visible absorption spectroelectrochemistry at functionalized transparent nanostructured electrode is an easy to operate. It's a quantitative, it's a real-time operando methodology. It allows to get better understanding of electrochemical reactivity of this kind of electrodes by allowing to investigate different processes and reveal local effects such as, for example, charge storage. And this is another example about a local pH gradient that I will not enter into details today. And I just want to finish to thank all the people that worked in the development of this methodology and the studies, especially also our collaborators in Canada, others in Paris for salt gel nanostructured electrodes, collaborators at ITODIS for Raman spectroelectrochemistry, because these electrodes can also be used for different kinds of visible-based spectroscopic measurements, our financial support, and you for your attention. Thank you.